Hi, in this video, we're going to discuss the fundamental theorem of calculus. In this video, we'll learn what the fundamental theorem of calculus is, we'll define the antiderivative of a function, and we'll use our knowledge of the fundamental theorem of calculus and antiderivatives to help evaluate definite integrals. So recall from the last video that we defined the definite integral in terms of Riemann sums. So we were approximating the area under a curve, the signed area, by using these Riemann sums. So the definition of the definite integral is in terms of Riemann sums. Now, unfortunately, these sums that you see here, they're really quite difficult to work with by hand. So, for example, if you wanted to find, the integral from 0 to 4 of sine of 3x dx, for example, that would be pretty difficult to do using this limit definition. You need to take the limit of this sum. The sum would have things like sine of 3ti, where ti is some point chosen in between some delta t interval. It's very difficult to work with to actually compute things. So we have this definition, which is sort of a nice theoretical construct, but it's very difficult to work with for practical purposes of actually calculating these things. We saw in the last video how we could calculate some of these simply by thinking about the signed area. But if you remember, those examples were primarily linear examples where we could sort of draw the function and use some basic geometric principles to calculate the area. So eventually we'd like to get something a little bit better so that we can calculate the definite integrals of more complicated functions. So let's start with the fundamental theorem of calculus part 1. So there's a part 1 and part 2. It's not particularly important that you remember which one is labeled part 1 and part 2. These are sometimes referred to as the first fundamental theorem of calculus and the second fundamental theorem of calculus, but we'll just collectively refer to these two things as the fundamental theorem of calculus, parts 1 and parts 2. So the first part of the fundamental theorem of calculus deals with this function a of x, which is called an accumulation function. So the theorem says, assume we're working with a continuous function f on some interval ab, and we want to define a function a such that a of x is equal to the integral from a to x of f of t dt. If we define the function a in that manner, then that function is continuous on the closed interval ab, differentiable on the open interval ab, and most importantly, the derivative of that function a at x is equal to f at x for every x in your interval. Now, this function a is called the accumulation function because if you imagine some function f that's defined at least on an interval a to b, then the accumulation function returns the area under the curve between a and x. So for example, let's say that this was 3 and maybe this x was 2, then a of 2 would be equal to 3 precisely because the integral from a to 2 of f of t dt is equal to 3. And then obviously you could go up a little bit more, say to x is equal to 3. And then maybe you've added on some more area. So maybe here you've added on 2 more units of area so that the total area is now 5. And then you would know that a of 3 was equal to 5, precisely because the integral from a to 3 of f of t dt is equal to 5. So this function a is what's called the accumulation function. And really, the interesting part is that as long as f is continuous, this function a is also continuous, but even better than that, it's differentiable. And most importantly, the derivative of this function a is just the function f that you were integrating. So let's take a moment to justify, this isn't really formally a proof, but to think through why this makes sense. So again, let's consider this accumulation function. So we have some function f, and far. Have this function f. And let's say here is a, and here is some point x. So at some particular point x, a of x would give me this area. Okay. Now, if we want to understand the derivative of a, then thinking back to calculus 1, this should be the limit as h goes to 0 of a of x plus h minus a of x all over h. Now, if we think about this quantity at the top, a of x plus h would be like if we imagine that, slightly different color here, there's some point x plus h just above x, okay? And then a of x plus h would be the entire area inside here, okay? So this region right here in the middle, this difference would be a of x plus h minus a of x. Sorry, I know that might be a little difficult to see there. Let's see if we can. A of x plus h minus a of x. So in particular, if I think about approximating this little area, well, if I'm using a left-hand rule, I would approximate this by just one little rectangle whose height would be the function value at this point. So this would be f of x, and whose base would be h. So while this quantity, a of x plus h minus a of x, is not exactly f of x times h, as h gets very small, it should be very close. So this should be roughly x of x, f of x times h, that difference. And now we can cancel an h in the numerator and denominator. In general, you should be concerned about whether those are 0 when you cancel, but we're taking a limit as h goes to 0, which means we're not actually concerned with what happens at 0. So this is the limit as h goes to 0 of f of x, but now notice that this doesn't depend on h at all. And so the limit as h goes to 0 of this, which is a constant as far as h is concerned, is simply f of x. Okay. Now, there's some hand waving going on in this step, okay? And in further mathematics courses, you might deal more rigorously with that justification. But for the time being, this isn't, again, a formal proof, but rather a rough justification of why the first part of the fundamental theorem of calculus is true. So this function a of x, again, is a very nice function. And in particular, it's what we're going to define as an antiderivative. So it's an example of something called an antiderivative. So given a function little f, if a function capital F is a function such that capital F prime of x is equal to little f of x, then capital F is called an antiderivative of f. So if you're given a function, say you're given the function cosine of x, the antiderivative of that function, so you've got f of x, say, is cosine of x, then the antiderivative of that function is a function whose derivative is cosine of x. So it's like differentiation, but in reverse. So its antiderivative is simply sine of x. Why? Because if I look at capital F prime, the derivative of sine is cosine. And so when I differentiate that, I get back to the function little f. Okay. So what we've seen is this accumulation function A is one example of an antiderivative function. But what this definition doesn't say is whether there's only one antiderivative function for a given function, whether there has to be an antiderivative at all, or whether there might be many possible antiderivative functions. So let's look at a couple of examples to get started. Now, in general, in math, there's this sort of trend that it's actually quite easy to verify whether or not something is an antiderivative, but it's very difficult to find the antiderivative if you don't have a good guess. So, for example, this is true with like finding solutions to different types of equations you might have seen in an algebra or pre-calculus course. It's very easy to check whether or not something is a root of a given polynomial. You just plug it in and see if you get 0. But if I give you a polynomial and ask you to find the roots, that problem can be rather difficult. The same is true of antiderivatives. So in this first case, we're given a function capital F and asked whether or not it is an antiderivative of this function little f. Well, that's easy enough. I simply need to calculate the derivative of capital F and see whether I get the function little f. So given my capital F here, if I look at capital F prime, I'm going to have to apply the chain rule here to calculate the derivative. So I have sine of x squared. So my outer function is sine. I'm going to differentiate sine. So the derivative of the outer function is cosine, and I'll evaluate that at the inner function times the derivative of the inner function x squared, which is 2x. So in fact, we would more typically write it in this way. And we can see that this is, in fact, little f of x. Okay. So capital F is an antiderivative of little f, precisely because when we take the derivative of capital F, we get back to the function little f. But again, that's just verifying that something is in fact an antiderivative. What might be a little harder is to find an antiderivative of a given function. Now, we're going to learn lots of methods for finding antiderivatives. In fact, we're going to spend at least the first several videos in this course covering what are essentially methods for finding antiderivatives of functions. But let's sort of start first with some fairly basic principles. My goal is to find a function capital F so that when I take its derivative, I get secant of 2x, tangent of 2x. Now, if I think back to my Calculus 1 knowledge, I might remember that there was some function that when I took its derivative, I got something like secant of something, tangent of something. Okay? And so if you think back, you might go, oh yeah, I think the derivative of secant of x was secant x, tangent x. Now, that's not exactly what I have here. Right here, I have secant of 2x, tangent of 2x. So I might just guess maybe I should try secant of 2x, right? So let me first sort of start by guessing. So what if I guessed that capital F of x was secant of 2x? Okay. Well, now if I was going to take its derivative, I would need to apply the chain rule. And so I would need to say, okay, derivative of secant is secant of 2x times tangent of 2x. So derivative of the secant function evaluated at this inside function. But then I would need to multiply by 1/2. Okay. Now, this is not my function little f. So this is not an antiderivative. However, sort of by looking at this, I might sort of get a clue of how, sorry, as I multiplied by 1/2, I should multiply by the derivative, which was 2. In either case, this is not f of x. Okay. But this sort of gives me a clue for how I might fix this. This 2 is the problem. I'd like to get rid of it, and I have a big product here. So what if I multiplied everything by 1/2? So what I'm going to do is I'm going to go back to my original guess for the antiderivative, and I'm going to multiply that guess by 1/2. So instead, I'm going to try 1/2 times secant of 2x. So now with that guess, if I go to take the derivative, Well, that 1/2 is a constant multiplied out front. It's just going to hang out while I take the derivative. Now, derivative of secant of 2x. That's secant of 2x times tangent of 2x times the derivative of the inside function, which is 2x, or sorry, which is 2. The inside function is 2x. The derivative is 2. And now this 1/2 and this 2 multiply together to give me 1, and I just end up with secant of 2x, tangent of 2x, which is my function f of x. Now, earlier I raised this question. I've now found an antiderivative, but are there other antiderivatives? So I might sort of initially think, well, no, because the only way to sort of get the function part here, the secant tangent piece is, well, you need secant here. So it's not like that's going to end up being sine or something, right? But an important piece, in fact, maybe one of your favorite facts about derivatives, right, is that the derivative of a constant is always 0. So notice that if we had added a 4 here, then this derivative calculation would have been exactly the same, except I guess we'd have a plus 0 here, but that would just go away, and we'd still end up with this. So here's another antiderivative for our function secant 2x, tangent 2x. And you might very well guess there's nothing special about 4. I could have added 5 or 17 or pi over 6. I could have subtracted 72, right? I could essentially have added any real number here, and I would have had an antiderivative for this function. So typically when we talk about antiderivatives, even though we may only write one representative down, we're really talking about a family of antiderivatives, which are that one representative we've written down plus or minus any constant you might want. Okay, so if a function has an antiderivative, then it's going to have infinitely many antiderivatives because we'll be able to add and subtract any constant we want. Now, all of this is good and well, but we sort of stated at the beginning that our goal was to evaluate definite integrals, and in fact, we've done nothing of the sort so far. So we ought to, sorry, before we get there, let's actually take a second for a quick knowledge check. So I want you to try and find an antiderivative for this function. F of x is equal to sine of 4x. And then I want you to ask yourself, is f of x is equal to negative 1/4 cosine of 4x plus sine squared of x plus cosine squared of x, an antiderivative of this function little f? So pause and take a moment and see if you can find this antiderivative. All right, great. If we're simply looking at the problem of finding an antiderivative of this function, we might first sort of say, okay, well, I need to end up with sine of 4x. And let's see, what gives me a derivative of sine? Well, the derivative of cosine is negative sine. So I might first try negative cosine of 4x. But if I do that and then take the derivative of capital F, then I will end up getting 4 sine of 4x, which is, of course, not little f. But then I could say, I see I need a factor of 1/4 to cancel out that 4 here. And so, in fact, I want to guess negative 1/4 cosine of 4x. And that will end me up with sine of 4x, which is my function little f of x. So there's an antiderivative of this. And of course, you could also add any constant you want here. Now, you may be tempted in the second part of the question where I ask if f of x is equal to negative 1/4 cosine of 4x plus sine squared x plus cosine squared of x. You might be tempted to say, well, that's not an antiderivative. There's sort of this other function stuff here. But with trig functions in particular, we have to be a bit careful because there are lots of identities that relate trig functions to one another. So in particular, in that example we're looking at, there are actually sort of two ways to think about this. So the first would be to say, well, let me just check whether or not this is an antiderivative. So if I were to just take the derivative, okay, well, I know this part is going to give me sine of 4x. I've already checked that part. Okay. Now here, if I take a derivative, okay, this is really sine of x squared. So this is going to be a chain rule problem. So this is going to be 2 sine of x times the derivative of sine of x, which is cosine of x. And the derivative of this piece, this is really cosine of x squared, right? So the 2 is going to come down, cosine of x to the 1, times the derivative of cosine of x, which is negative sine of x. And now if you notice, these two will add to 0. And so, in fact, we'll just be left with sine of 4x plus 0, sine of 4x. So in this case, this is, in fact, an antiderivative. Now, another way to see this would be to observe that there's a trig identity that tells us that sine squared of x plus cosine squared of x is, in fact, just 1. And so really what we have here is our original antiderivative we found plus a constant, which will still be an antiderivative. Now, again, with trig functions in particular, we need to be very careful of this fact. Sometimes trig identities can trick us into thinking that something is or is not an antiderivative when in fact it's the other way. All right, now let's see if we can leverage this knowledge of antiderivative functions into calculating definite integrals. And this is where the second part of the fundamental theorem of calculus comes into play. The second part of the fundamental theorem of calculus says that if f is continuous on a closed interval ab, and if capital F is any antiderivative of little f, then the integral from a to b of little f is equal to the function capital F evaluated at b minus the function capital F evaluated at a. This is really a miraculous fact when you think about it. If you look at the left-hand side here, this is a definite integral. This is defined in terms of limits of Riemann sums. On the right, these are an antiderivative function evaluated at 2 different points. This is something to do with derivatives. This is a limit definition that has nothing to do with Riemann sums. So on the surface, these two things have absolutely nothing to do with one another. But the sort of miraculous fact, and why, in fact, it is one of the fundamental theorems of calculus, is because it relates to us that there is this connection between definite integrals and derivatives, or in this case, antiderivatives. So practically speaking, this is very, very useful because now if we want to calculate a definite integral, if we can find an antiderivative of the function we're integrating, then it'll be very straightforward to calculate the definite integral. Let's see a couple of examples. Okay. Oh, sorry, before we do that, let's first actually justify like roughly why this is true. Okay. So let's say first that we chose as our antiderivative function that accumulation function that we talked about earlier. Okay, so if we were to do that, let's think about what would capital F of B minus capital F of A, like what would that equal? Okay, so capital F of B, that would be the integral from A to B of f of t dt. Okay, and then minus capital F of A, that would be the integral from A to A of little f of t dt. Okay. Now, if I look at these, okay, this is just, the integral from a to b of f of t dt. This is an integral from a to a. That's like asking how much area is under the curve, but your base is 0, right? So this integral, in fact, is 0. And so this is just equal to the integral from a to b of little f of t dt, which is precisely what the second part of the fundamental theorem of calculus claims. It claims that f of b, capital F of b minus capital F of a should be equal to the value of the definite integral from a to b of f of t dt. Okay, but again, we need to be a little careful because the fundamental theorem of calculus says this should work for any antiderivative, not just the antiderivative that is this accumulation function. So we could then modify our question slightly and say, okay, well, what if G is any antiderivative? Well, if G is any antiderivative, then, well, G is going to be equal to that accumulation function plus some constant. So in that case, we have that G of B, that's just going to be F of B plus some constant, minus G of A, that's going to be F of A plus some constant. And now constant minus constant, those are going to cancel. And so I'm just going to be left with capital F of B minus capital F of A, which we've already shown up here is just equal to the integral from A to B of little f of t dt. So in fact, for any antiderivative function, if you take that antiderivative and evaluate it at the two endpoints, that will give you the integral from A to B of the other function that's sometimes referred to as the primitive function, little f of t. All right, so that's why it's true. Now let's see the fundamental theorem of calculus part 2 in action and actually use it to calculate some definite integrals. All right, so let's say we want to find the integral from 0 to the square root of pi over 2 of 2x cosine of x squared dx. Now, this may look very intimidating on the surface. You have square roots of pi's over 2's. You have 2x cosine of x squared. But let's just go back to the fundamental theorem of calculus. The first thing I need is I need an antiderivative of this function here, right? So I need an antiderivative of this function. Well, if you recall back, we already saw an antiderivative of this function. So this is my little f of x. And we found an antiderivative function for this, or observed that the antiderivative of this is sine of x squared. So by the fundamental theorem of calculus, this integral from 0 to the square root of pi over 2 of 2x cosine x squared, well, that ought to be equal to this antiderivative function evaluated at the upper limit of integration minus this antiderivative function evaluated at the lower limit of integration. And now if I do a bit of simplification, this would be sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. This is 1 minus 0, or just 1. So again, the only real difficulty here is you need an antiderivative. But if you can find an antiderivative, then essentially it just becomes evaluating a function at some points. Now, we will sometimes use a little bit of shorthand. So here, when we talk about evaluating it at the two endpoints, we will start writing this in the following way. So once I find my antiderivative function, I'll use this notation with a bar. And what this notation means is I'm going to evaluate it at this point, and take a difference, just as I did before. So then again, I would just write sine of square root of pi over 2 squared minus sine of 0 squared. But as we go along, when we just want to write down our antiderivative function and show that we know where to evaluate it, we'll use this sort of notation, and we'll see that modeled again in a minute. All right, here's another example, and we haven't sort of maybe seen this before, so this will give us an opportunity to work through some things and apply some properties of integrals that we saw in previous videos. So now I have the integral from pi over 8 to pi over 4 of 1 plus sine of 4x dx. So in this case, the first thing I want to do is use a property from earlier. So I want to use the fact here that I can break up the integral over the sum. So I can rewrite this as an integral from pi over 8 to pi over 4 of 1 dx plus an integral from pi over 8 to pi over 4 of sine of 4x dx. Now I can calculate each of these independently and then come back and add them together. Okay, so let me first focus on this integral here. Okay, so if I want to evaluate this integral, the first thing I want to do is I want to find an antiderivative of the function 1. So I want a function whose derivative will just be 1. Okay. That sounds to me like the function x. So the antiderivative is just x, and then we're going to evaluate it at pi over 4 and pi over 8. So that's going to be pi over 4. So when I evaluate the function x at pi over 4, I get pi over 4 minus evaluated at pi over 8. Now if I need to subtract those, pi over 4 is the same as 2 pi over 8. So I'm just left with pi over 8 for the value of this first integral. Okay, so this first integral is equal to pi over 8. Now I need to deal with this second integral, and the first thing I need to do is I need to find an antiderivative of sine of 4x. Right? Well, we've already seen this piece before. So now as I go to deal with the second part, I need the integral from pi over 8 to pi over 4 of sine of 4x dx. Well, that's going to be my antiderivative function, which we've already seen before. That's negative 1/4 cosine of 4x, and I'm going to evaluate that at pi over 4 and pi over 8 and take a difference. Okay. So let's see, if I evaluate this at pi over 4, I'm going to get negative 1/4 cosine of 4x evaluated at pi over 4. The 4's will multiply or will divide to give 1, and I'll just be left with cosine of pi. Then minus evaluated at pi over 8, I'll get negative 1/4. Actually, move this down a little bit. I get minus negative 1/4 cosine of 4 times pi over 8 will give me pi over 2. And so what I'll end up with here, let's see, cosine of pi is negative 1. So I'll have negative 1 times negative 1/4. That'll give me 1/4. Then here, let's see, I've got cosine of pi over 2. Cosine of pi over 2 is 0. So this whole term is 0. And so I get my final answer of 1/4. So in this case, I get pi over 8 plus 1/4. If you really wanted to, you could combine these with a common denominator. This would be pi plus 2 over 8. I am actually perfectly content with you leaving that as your final answer. In fact, it's often easier to understand what you did if you leave these separately. But if there is some reason why you may want to combine them, you certainly can. You wouldn't be counted off on any assessment for simplifying it more, but I'm also perfectly fine with you leaving it this way, and you wouldn't be penalized for leaving this in this form. All right, and now it's time for another knowledge check. So now I'd like you to stop and evaluate the integral from 0 to pi of cosine 2x plus 3 dx. Okay. Now, in this case, we again have an integral of a sum. It would probably be nice to break that integral up. So we can think of this integral, in fact, maybe I'll just write it off to the side here. We can think of this as being equal to the integral from 0 to pi of cosine 2x dx plus the integral from 0 to pi of 3 dx. Okay. Now again, we'll take each of these parts in turn. So in the first part, if I want the integral from 0 to pi of cosine 2x, then I need to find first an antiderivative for cosine of 2x. Now again, you might sort of think, oh, sine of 2x would work, but the derivative of sine of 2x would be 2 cosine 2x. So you need a factor of 1/2 to help you out. So the antiderivative will be 1/2 sine of 2x. And then we will evaluate that at pi and 0 and take the difference. So if I evaluate this at pi, I get 1/2 sine of 2 pi minus 1/2 sine of 0. Sine of 0 is 0. Sine of 2 pi is 0. And the value of this integral is 0. So we get that this first part is 0. Now let's look at the second part. So looking at the second integral, we want the integral from 0 to 3 of, or sorry, 0 to pi of 3 dx. So the first thing we need is we need an antiderivative of 3. That sounds like 3x. Okay. We're going to evaluate it at pi and 0 and take a difference. So that's 3 pi minus 3 times 0, or just 3 pi. So we get plus 3 pi there. So we have 0 plus 3 pi for a final answer of 3 pi. That concludes our video on the fundamental theorem of calculus. Hopefully now you have a better understanding of the fundamental theorem of calculus, how it relates differentiation and integration, and most importantly for the purposes of our course, how it is very useful in calculating definite integrals. As you can see, however, it essentially takes the difficulty of finding a definite integral and converts it into a difficult problem also of finding an antiderivative. You've seen examples where so far we've been able to calculate antiderivatives, but for more complicated functions, that's highly non-trivial. And so throughout the next several videos, we'll learn several different methods for calculating antiderivatives in order to then calculate the definite integrals of different functions.